Hello, my name is Jacob Cassidy. This is my final presentation for application of sensing systems. I named my project LORAD, and the broad goal is to develop a robust optical relay decoder. And then I'm, arguing that this can be applied to lunar environments. Yeah, so on the lunar surface, there are times where, at least in kind of our goals, that there will be times that there'll be a rover, there'll be a lander, they want to communicate with each other, they don't share power or data links with each other, and maybe RF emissions are like broken, or for some reason, maybe it's a crowded place that they don't want to use that, and instead they would like to use something more directed, like an optical sensor. The problem is with optical sensors that it's pretty common that you might miss a bit, and if you miss a bit, then you typically have to throw the byte out, and then given how frequent the missed bits are, um, you often end up throwing entire transmissions out because they don't pass, the CRC8 check or something like that. So yeah, the sensing is required because you need some type of receiver circuit to receive the information that's being sent between these agents. And my goal here is to characterize and describe how I enhanced the transition capabilities of these optical sensors using a machine learning model. And I initially started with the goal of characterizing a distance-based estimation as well, but I ran into troubles with my op amp oversaturating at even short distances. Yeah, so my system has kind of three main agents. You could think of them. I have a beacon that has this TSAL 600 IR emitter, and the traffic light that's used for debugging, as well as an HTTP server for injecting new messages. I have a receiver, which is another Pico 2W. It has two BPW34 photodiodes. Um, and yeah, I'm applying a high pass filter to those. And then I have the decoder, which is running on my computer. It's using a hidden Markov model and the Viterbi algorithm to enhance the number of bits it receives. Um, and yeah, so the signal conditioning is as follows. So I take a sample from each of my ADCs. I pass them through high pass filters. Then I sum the two, and then I have a threshold, which is adaptive. So, I'm looking for spikes in data, so I, take the average um, to make sure that I'm actually seeing a spike. And yeah, again, the traffic light is used on the outside to kind of show that the transmitter is sending data. Since I can't see the IR emitter firing with my human eye. Yeah, so how the data acquisition works, for the receiver is shown over here on the right. So each of these messages is encoded in, different length pulses, where a start pulse is 50 milliseconds. A 0 is represented as 10 milliseconds. All idle time in between pulses is, the same, and then a 1 is represented as a 25 millisecond pulse. And if you look below that, still on the right, you'll see, kind of what the signature looks like when you zoom in. And that, there's times where you might miss detecting a pulse, well, that's just fine because as you can see, you should be able to back calculate what the size of that pulse was that was lost. And this is what this learned hidden Markov model is doing. You can see the structure for the hidden Markov model to the left. Um, to the left of my picture. There's a start bit and then 8 bits and then another start bit, and that's the transition of the model. And those values, have two transmission or transitions. One could be a 0 and one could be a 1. Um, and yeah, this can be represented as a lattice structure where that you should be able to recover the connection between that lattice. And yeah, the features that I use for training is the width and gap of each of the previous falling edge. Um, and this information is sent along with the number of bits to help backtrack things. Um, and yeah, for my to train my model, I took 600 tests, three of which transmissions were corrupted in some way, so I was able to keep 597, and I did this over 5 different rates, which you can see the bits per second there. I drove my beacon over HTTP for these tests. Um, and yeah, I use some English messages. I use some random ASCII to train the model in different ways. And when I trained my model, um, I held out some of these messages and compared them to the output. So yeah, I'm trying to predict a byte given or a bit given a previous transition state. This shows the results of my transmitter and receiver with and without um, the decoder model that I showed on the previous slide. So on the left here on the table, you'll see that the threshold is just me looking for the pulses, and then what I'm calling sequence is the hidden Markov model's output. So in my test, 72% of the messages were a success, and this is the entire message. After using the hidden Markov model at this low bit rate, I'm able to get 100% accuracy. Which is significant, a very significant improvement, and a reduction in character error by 1%. If you look at the next speed, so now I'm doubling the speed that I'm transmitting. I'm only able to get to 72% with the hidden Markov model, but still a massive reduction, almost 20% of the character error that we were seeing before. So yeah, this this decoder significantly improved the ability of the receiver to get the full message. Um, and yeah, I mean, one thing to note is that this decoder was too large to fit on the Pico, so there's a cost to this improvement, and that's more processing in between the messages. Yeah, so this is from my demonstration that I submitted. You can see on the left here, I'm typing in a new message, hello world. On the right, you can see that some of the messages were decoded perfectly the first time. Some like this one that you just saw, the A is corrupted there in and space is corrupted there in world. So the decoder is working very well to improve the accuracy of the receiver.